All right, thanks. So it's the last talk of the evening, but we had one that wouldn't show up, so I have like half an hour, 40 minutes? Okay. Excellent. Good. Because I know you're not looking forward to anything else. I did want to start perhaps on a more philosophical level. So the past, few nights I've been lying awake at night wondering why am I here? But particularly in this session. So, because the observations I show, I think more relate to ionospheric plasma, the ionosphere being a source of plasma for the magnetosphere. Not so much the global modeling. But I was thinking, well, maybe, I'm talking about things around the moon. Maybe it's sort of on the last talk of the day. Maybe it's sort of this in between the Earth and the planets we'll talk about Thursday, Friday. Because, we were partway there. But there's already been some comparative planetology stuff. And then I started to think, well, maybe we'll be talking about observations. And some of the other talks today during this global modeling part had some observations, including John Merriweather's talk just before this. So maybe these are the types of observations, the types of data that need to be validated by your global models. Or you could look at the other way and say, maybe this is the kind of observations and data that models can help us interpret and explain. So I finally came to at least I was comfortable with myself and was able to get some sleep. My existential crisis was over. So let's see. Before we start, I also want to point out this lovely picture from Monday, taken by Carol Patty, of our lovely venue and Half Dome and all that. But I want to point out this little guy up here. Ooh, where'd he go? Well, up there. Here's the moon. Oh, there it is. Haha, the moon. Right. Thank you. And so this is a couple days before full moon. Full moon is Friday. But for about a week or so every month around the full moon, the moon is in Earth's magnetosphere. And so say, for example, you have some satellites orbiting the moon, looking at things like acceleration or reconnection or turbulence or electrodynamics of the moon in space. You're also going to be measuring those things in the magnetosphere for about a week per month. And that is exactly what Artemis does. And so I'm going to show some Artemis observations of what seem to be oxygen in the deep tail around the moon. And Artemis, in case you're not familiar, was part of the Themis program. Themis was 5 satellites. They took 2 of them, sent them to the moon, and they called that part Artemis. And it studies the acceleration, reconnection, turbulence, electrodynamics of the moon in space. So, Vasilis has some great acronym abilities, I tell you. And so we think that we're seeing oxygen ions in the vicinity of the moon. So presumably, these come eventually, ultimately, from the ionosphere. But they have several keV energies, which is a lot higher than what I've heard from many of the outflow talks earlier in this past 3 days. And so how do we get energies that high? Interesting thing about Artemis, there is no mass composition measurements. And so we're inferring that these are oxygen based on secondary peaks in the ion flux. So I'll show some spectrograms in a bit. And I have 2 examples where we see O+, and it looks to be O2+, which is kind of cool. Let's see. And then there's still some open questions we'll address near the end, is how does oxygen reach all the way to 60 RE? I've not seen much in any of the talks that consider things much further than a few RE, except some of Vahe's simulations. At least he went out to like 40 RE, and there was still oxygen out there, so that's helpful. And then how do we get energized to the energies that there's a few keV, not a few EV? And why do we want to do this in the first place? Well, there's been lots of talks already that this stuff can impact the magnetospheric dynamics. The question mark doesn't mean we don't know. Well, it means there's a multitude of ways. So pick your favorite way that you can impact dynamics. You can either increase reconnection or decrease reconnection. You get all this mass loading, all sorts of interesting stuff in the magnetosphere itself. But also, some people are interested in the moon. And so we have that also affects the lunar exosphere. So I'll take just a minute, maybe 30 seconds, and talk about that near the end. So how do we get into this? So basically, we stumbled upon this. We're actually looking at what's going on around the moon, what's going on There was some thought in the magnetosphere. We were trying to get at magnetospheric convection using the moon as an obstacle. But looking at the data, we still saw these pesky little secondary ion peaks sometimes. Oh, I see. There's 2 buttons. I just figured that out. The top button is the good one. And so we thought, well, what could these peaks be? We saw these quite a bit, about once per month. We have very, very rough statistics. I wouldn't even call them statistics, but we see them sometimes. And so we said, what's the source of this secondary ion peak here? Could it be due to different species? And could they be coming from the ionosphere? Right now, we think, yeah, that's possible. And then can we determine some of the properties, like the mass, the density, the velocities of all and the occurrence probabilities of this sort of feature? The answer is, well, probably, but we just haven't done that yet. But there's lots of work still to do. And so thus far, we've done it the easy way, where we visually inspect. We look at the spectrograms from Artemis and see if we can notice the secondary peak. What makes it nice is that we're only looking in the magnetotail. So that automatically removes 3/4 of the data. Because the other 3/4 of the time, the moon's in a solar wind, and we don't see this type of thing. We can't see evidence of the ionosphere. And so right now, it's just subjective. We look for a noticeable band above the normal flux. So again, here's just the example. This little thing up here. Hey, look, that looks different. And it turns out these are easiest to find in the lobe and plasma sheet boundary layer, where you don't have the messiness of the plasma sheet itself. Let's see. So it's an interesting point. So the Artemis has these electrostatic analyzers. They measure energy per charge. They do not measure mass. So we have to make some fundamental assumptions that if we assume all the plasma has the same velocity, flowing to the same velocity, then the more massive particles have a higher energy, and that is proportional to the mass. And so we determine a mass from the energy shift with this assumption that they'll move in the same velocity. And we'll address, is that really reasonable or not? And maybe. So here's first example, lots of data. Let's see, so we have magnetic field, density, velocity, temperature, ion, electrons. And so this is from the 2 Artemis spacecraft, Probe 1 and Probe 2, which were Old Themis B and Old Themis C. And so in this case, we seem to be in what I consider the plasma sheet boundary layer. Let's see, I'll move to the next slide. Remember the pictures, I have words here that tells us more about where we are. And so the magnetic field, generally in the x direction, so we're in the tail. Fairly, not too bad densities, and we're not in the lobe. The lobe would be much lower densities, so that's why I consider it boundary layer. And there's about less than 100 kilometer per second velocity of the ions, about 100 eV ion temperature. And so again, this isn't the cleanest one, but here we see the main peak of the ions. We presume that's hydrogen. And then up here we see a fainter peak that we think is something else, another species. And so what do? Well, we calculate where the main peak is. So the normal main peak in flux, what energy is that? And we guesstimate and say, okay, it looks like it's about 16 times higher, so that's the black line. And so the red line is just multiply it by 16 and see where that lies in the spectrogram, and it seems to match it pretty well. And so we infer that this secondary peak then is due to singly charged oxygen. And we actually look at some of the slices through the spectrogram, so it actually did a little more quantitative, and say, yeah, so here's the oxygen. There's a secondary peak here at 16 times energy, and we see that in both Artemis probes. And so it's not inconsistent with oxygen. Let's see. Oh, and even look at the direction. So these are looking at angular spectrograms. And so we look at the lower energy component. That's here, presumably the hydrogen. And we look at the direction those ions are moving. They're moving at 180 degrees. That means they're moving tailward. And they're field aligned, since magnetic field was in the minus x direction, which is consistent with that about 100 kilometers per second velocity that was measured from the moments. And there's a higher energy component that's up here, so we've separated it out. And it's broader, but still generally tailward. And so this is also consistent with our assumption that both populations are moving together. And we're just looking at different energies that mean different masses that move at the same velocity. Okay? Second example, this one's a little bit nicer, a little bit cleaner. There's the data. So again, the same format. Let's jump ahead. Actually, I want to point out there's a little blip here where it actually looks like we enter the magnetosheath, where the magnetic field starts jumping all around. The density increases to about 10. Your velocity increases, becomes more negative, about 400. And so there's a little section here is magnetosheath, but on either side we're still within the magnetosphere. So some sort of boundary layer near the magnetopause with one big magnetosheath excursion. And so again, magnetic field's in the next direction, this time positive. We have densities in order to 1 to 0.1 when we're in the magnetosphere, higher in the sheath. And then again, velocities are fairly low, 200, 100, 200 kilometers a second when you're in the magnetosphere. So similar to last time in general properties, but it looks a little cleaner. What's interesting, though, is we identify the energy of the main peak. We say, okay, is this other peak 16 times higher? Not quite. Turns out it looks like it's more like 32 times higher energy. And that light's right on top of the secondary peak. And again, I'll show the cuts through the spectrogram. So the main peak, we assume that's hydrogen. Dotted line is 16 times. So that would be where atomic oxygen would be. And this dashed line then is 32 times the main energy of the main peak. So we say, well, that's could be O2 plus, or it could be NO plus. I mean, that's still close. That'd be 30 times energy, 32 times. Or it could be something like sulfur, but I highly doubt it because we're at Earth, not at Jupiter. And look at directions. And again, the directions are both the hot and cold component going the same direction. So they seem to be moving together. So again, that's relatively consistent with our main assumption. So here's just the summary again, repeated. So we think we're seeing oxygen in the tail from Artemis. We think it's from the ionosphere because it's oxygen. So the secondary peaks in ion flux. And so this only works. This is our assumption if the ions flow with the same velocity. Well, they're going in the same direction. That's true. But they're not going perpendicular to the field. They're parallel to the field. And I could imagine that if it's perpendicular to the field, you could see the same. It's easier to see how you get the same velocity due to convection. If you're going parallel to the field, it's a little bit tougher because there's lots of processes that could give the different components of the plasma the same energy, but we're seeing them at different energies. So that means giving the same velocity, and they're dispersed in energy. Or you could also say that, well, maybe they're actually not. Maybe they're both hydrogen, just different populations. But then why would the energies track so well? So this is sort of a conundrum. We see the velocities parallel, and that's not clear why this would be going parallel to the field if we're looking at a velocity filter. And also the two examples, we see O plus, we think, and O2 plus. So how do you get it out of the ionosphere? Been lots of talks about that already. Upflowing and acceleration and all sorts of different mechanisms. Many of those related to geomagnetic activity. So if we look at geomagnetic activity, then for these two intervals, especially for the second interval, we see this nice clear, appeared to be O2 plus. It's about 1,000 nanotesla AE peaks, a little bit higher than that. For the first interval, we have another more activity, a few hundred nanotesla. But what I thought was kind of weird is why do you see O2 plus in the second interval, but not O plus? So if you see molecular oxygen ions, why not atomic oxygen ions? But it could be whatever drift paths those plasma take to get there is good for one and not for the other. Another conundrum, I would say, open question there. So how do we get it out there? How do you reach 60 RE? And how do you get it energized to hundreds of kilometers a second? So this open question, I had some crazy speculation today. Well, let's see. Maybe we can get this. Actually, so let me preface this. I have no idea yet. Just some thoughts, and we can hopefully have some discussion about that. If the ions make it near the magnetopause, they might get swept up a little bit. It's just a heuristic way of you might get some motion tailward by sheath flow or boundary layer flow, and eventually they can convect in back into closer to the more central part, not the central plasma sheet, but away from the boundary at least a little bit. And we're going to observe them as we saw with Artemis. And where would they come from the high latitude? Actually, they got the day side and come back around the flanks. I don't know. Again, crazy speculation. Let's see what else. I don't really know about this. Magnetospheric dynamics, we all know that can impact magnetospheric dynamics. What I think is going to also impact the lunar exosphere. And so these ions hit the surface of the moon. They give off a puff of neutrals. That creates the moon's exosphere. It turns out that scales with mass. So the higher mass particle you have, the more exosphere you create. So O plus is much more efficient than H plus. O2 plus, much more efficient than O plus. So you may see a pumping up of the exosphere during these events where these heavy ions are hitting the moon. And so, final slide. What's next? There's a whole bunch more to do. I mean, this has just been a first look at, hey, wow, this is neat. What does this mean? We need to do a lot more characterization with the mass and density and velocity of these ions. And where do we see them? When do we see them? Can we get with some probabilities and dependencies on this? And of course, if these things are related to sheath flow or boundary layer flow, we need to correlate that with what's driving it. So solar wind, IMF, even sheath velocities. And so there's still a lot of things to do. But I just wanted to say, hey, wow, I thought that was neat. That even at 60 RE, we can see evidence of Earth's ionosphere in the magnetosphere. I think that's it. Yeah. Oh, God.
Well, it's too bad Dave Hardy's not here because he would tell you that going back to the old Fogey network, back when we had instruments on the moon.
Ooh, yes.
Yeah, we actually saw this too.
Yes.
Very frequently. And Dave Hardy wrote several papers on it. And the model that we came up with was the velocity filter effect in the magnetotail. And what the statistics that he came up with was when there's a strong BY, if you're on the dawn side above the neutral sheet or the dust side below the neutral sheet, then you preferentially saw it. And it came out really quite well on those kind of statistics that you might want to look at. But then again, you beg the question, where did they originally come from? And there's a lot of head scratching, okay? Because if they're an ion fountain, you wouldn't necessarily expect them to see the same velocity as the hydrogen.
Yes.
So one model we came up with, I still don't know if it's true, but we came up with was if the plasma sphere. Yeah, that's what, I just used that word already if you weren't listening. Yeah, no, well, if they come from the same place, they'd have to be coming from the same field line. So I'm saying if they were at midnight, they wouldn't come up with the sheath that was at the cusp. Okay, fair enough. Well, in any case, there's been a lot of modeling that went on things like that with use the velocity filter effect. And one thought we had was that if the plasma sphere peels off and goes into reconnection, then it can provide heavy ions to recirculate through the reconnection and join the sheath. And if you have these tongues, like we saw, where the plasma
out the day side.
Yeah, going out the day side, then you can really populate, the heavy ions to get swept up into the solar wind. So,
I like that.
That's what we came up with in '77.
It's the top one on the pen.
Oh, thank you. Okay, naturally I endorse everything Pat said, and I also wanted to call your attention, though, to the Don Williams instrument on geotail.
Yes, it's warhead composition.
It's super thermal, but if you haven't looked at it, it did detailed composition and charge state. I remember Steve Kristen papers, for example, out to 240 Earth radii downstream, nitrous oxide, singly ionized, NO, NO2. There were other molecular ions detected, but it might help you, tweak out the science out of this.
No, this is good. That's good to remind me. I looked at briefly at those those observations from the instrument. Yeah, it's great stuff, and it's way the heck out there. Yeah, thank you. Yeah.
We're going to take Mike's question, Bill Peterson's question, and then I'm going to cut it off because we've managed to catch up to our closing time as if we hadn't lost the talk.
That was my goal.
So Mike and Bill's been waving his hands forever.
My main point was going to be, have you looked at geotail? And I'm glad that Jim just said that. So he said it to me too. So, but my other point there was that to go along with Pat Reif, not just the plasma sphere, but the entire plasma sheet goes out to the day side and enters the magnetosheath on the day side when it recirculates. So
Yes.
not just
Yes.
plasma sphere, but everything from the magnetosphere makes it out there.
So I'm not as old a fogey as Pat, so I'm going to I'm going to talk. Well, she's better looking, of course, but I'm going to remind Orsini and his colleagues in Italy had an instrument on IC 1 that was out in the tail about 20 RE, and they did a lot of statistics on these kind of things, and they attributed it to, as Pat said, a velocity filter effect. And I think if you do wind and the moon and geotail, you might be able to make a nice picture and actually say something about how ions get out from the magnetosphere and get blobs of ions get out.
Out to
Yeah, and there's
tens,
no problem. The
hundreds.
The O2 plus or NO are commonly observed when KP is above 3 for about 10 hours.
Uh-huh.
So if that's the case where you're at, then that's not a problem. There's a few papers by Yao back in the 80s and 90s that document that. Huh?
Comment from Alex.
Yeah.
I know it's going to be very
And rims and
Well, I
lots
thought
of-
I would start by reading a novel. But anyway, no, I know everyone wants to know, so I'll be fast. I was just going to say one of your concerns was about why should the ions be moving at the same speed. And one of the things, well, it's true that ions are constrained perpendicular to the field in their motion to move the same. They're not constrained parallel. It's not actually entirely true. They are constrained by two-stream instability.
Oh,
So you may
that's-
consider investigating the stability criteria given your local plasma parameters and see, if that can explain how they're limited in their motion. The other point I'd make is it's not quite true what you said earlier in your talk that we haven't done models of O+ from the ionosphere to the moon. I actually did some.
I don't know of any. How's that?
Well, I'm going to tell you about one.
But now I'm going to know about it.
So a colleague of mine at Goddard, Menelaus Sarantos, was looking at Kikuya measurements and was trying to explain whether the moon could itself be a source for some of these ion observations. And O+ was puzzling because he couldn't explain it with the volatiles and whatnot.
Right.
So we actually did some modeling for that particular day and those particular observations and estimated, roughly what order of magnitude you could expect around the moon at that time. So there is actually, in the models, evidence that O+ does get down there.
Yeah, but what energies were you able to get those?
We were just looking
Or
at
just looking at
abundances. We weren't,
get there.
We weren't looking at energies.
Okay,
for that,
okay.
So.
That's a good look up. Oh, okay.